Assalamu alaikum, dear students. Today is our lecture number 3, and the topic we are going to study in this lecture are as mentioned in the next slide. The content of the lectures are that we are going to cover today: the types of fluid, numericals related to viscosity that we will solve also, wetting and non-wetting liquids, surface tension, capillary and capillary effects that we will see, and compressibility of the fluid we will discuss in this lecture. So first of all, today that we are going to discuss it is type of fluid. So what are the type of fluid we are going to discuss? There are so many, but here we are going only to discuss the ideal fluid. So what is the ideal fluid? Ideal fluids are incompressible and inviscid. So what is the meaning of incompressible and inviscid? Incompressible means the density remain constant. If you apply the pressure, if you increase the temperature, the density will not change, it will remain constant. And the inviscid means there is no viscosity, that means there is no resistance offered by the fluid, offered by the ideal fluid. Where the real fluids are compressible and viscous. Okay, so the real fluids are basically two types. Real fluids we know, we all know in our daily life: the water, the oil, the honey, air, and all those fluids are real fluids. But in the real fluid also we have two types of fluids: Newtonian fluids and non-Newtonian fluids. Newtonian fluids are those fluids which follow the Newton's law of viscosity. So what is the Newton's law of viscosity? In the Newton's law of Newton says the applied shear stress is directly proportional to the rate of shear strain. So this is the Newton's law of viscosity as it is mentioned here. And in this case, the relationship between the shear stress and the shear strain are a straight line. So here we can see the here you can see there is a picture in which we can see the behavior of Newtonian fluids. First of all, the ideal fluid. So where this ideal fluid lies in this picture. So the ideal fluid, basically we know there is no viscosity. There is no viscosity. That means if the viscosity is 0 here in this equation, the tau is equals to mu du by dy. If the viscosity is 0, that means the shear stress is 0. So what is the viscosity line and what is the shear stress line? Because and du by dy, this is what? This is basically the rate of deformation. Okay, that means if there is no viscosity, that means it doesn't offer any resistance. So rate of deformation is also equal to the velocity profile. So basically this is the line where the ideal fluids are lies on. This is the horizontal line. At this point the viscosity is 0. Okay, so as the viscosity increases, the line start increasing, just like air. The gases have a less viscosity, so the air is lying somewhere here. The water has a more viscosity, so it is going up, and the oil has a more viscosity, so it is going up. So you can see all of them are a straight line. Okay, so if we compare this equation with a straight line, so what is the equation of a straight line? Y is equals to mx plus c. So here y is equals to tau, that is the shear stress, mx. M is equals to mu, that is basically the slope, and x is equals to du by dy, because the shear stress is directly proportional to velocity profile or shear strain, and plus c, since this curve is starting from the origin, so c is equals to 0. So that means if there is a shear stress, okay, so that means mu is equals to 0 and shear stress is 0. That means all ideal fluids will lie here. So in this case, the behavior of Newtonian fluids. So this is the behavior of Newtonian fluids. So air, oil, and waters are the Newtonian fluids. Now next move on to the non-Newtonian fluids. Non-Newtonian fluids are those fluids which do not follow the Newton's law of viscosity. So what are the Newtonian fluids? The Newtonian fluids, the non-Newtonian fluids are basically three types, for shear thinning, for shear thickening, and Buckingham plastic. So here we can see the behavior in the graph. Here we can see the behavior of non-Newtonian fluids. This is the Buckingham plastic. This is Newtonian fluids that follow a straight line, which follow the Newton law of viscosity, and this is pseudoplastic, and this is the dilatant. Let's see what is Buckingham plastic. Buckingham plastic, it is neither a fluid nor a solid. Such material can withstand a finite shear stress without motion. Therefore, it is not fluid, but once the yield state is exceeded, it flows like a fluid, hence it is not a solid. So toothpaste and mayonnaise are an example. So we all know, because whenever we take toothpaste, it doesn't come out itself unless we applied a particular shear stress on it. So there is this, for a particular amount of shear stress, once it is greater than the yield stress, the fluids come out. So that means to move such kind of fluids, we need to apply some shear stress. Without that shear stress, those fluid doesn't move. So here you see, this is the yield stress is required to flow Buckingham plastic fluids. Okay, so that's why we applied the force, it doesn't move. We apply the force, it doesn't move. We apply the force, it's not moving. But when it reaches to its yield stress, so the toothpaste or the mayonnaise that's come out from the outlet. So such kind of fluids are called Buckingham plastic fluid. Now the pseudoplastic, and the pseudoplastic fluids are also called shear thinning fluids. So what is basically the shear thinning fluid? Fluids that apparent viscosity decreases. Viscosity decreases with increasing shear stress. When we apply the shear stress, the viscosity decreases. The harder the fluid is sheared, the less viscosity is become. Examples are latex paint, clay, milk, and cement. Okay, so when we mix the because we know we have a latex paint, because from one box we make 4 boxes. Okay, so when we mix with the stick or something in a circular way, so we basically whenever we rotating in a circular way, what happens, we apply that means we are applying a shear stress in a circular direction, and because of that liquid moves round and round. That means liquid deformings till we stir the fluid or till we apply the shear stress on the fluid. So that means the latex paint, the clay, the milk, okay, the cement, if we are moving, if we are applying shear stress, their viscosity decreases. So let's see here the pseudoplastic. Here you see initially the viscosity was more. If you take it, the viscosity is going here. Okay, but when you are applying as the shear stress is increasing, the viscosity is getting decreases. Okay, because you see here is this is basically the line of the shear stress. This is the viscosity line, but as the shear stress is increasing, the viscosity is decreasing. Now next, for the shear thinning fluids, or it is also called a dilatant fluids. So what is basically the dilatant fluids? The apparent viscosity increases with the increasing shear stress. So as we increases the shear stress, their viscosity also increases. For example, the water and corn mixture, okay, water and sand mixture, because when we mix water and corn together, so as we applying the applies the shear stress, and we keep applying the shear stress, what happens? Their mixtures become thicker and thicker. So same we can see here. Initially the viscosity is following this line. Okay, you can see the viscosity is following this line, but as we are increasing the shear stress, the viscosity is increasing. So such fluids are called the dilatant fluids. So now let's move on to some of the example of viscosities. So in the problem number 1, the velocity distribution for the flow of a Newtonian fluid between two wide parallel plates is given by equation this. So this is the equation is given that the way the fluid is moving, okay, where v is the mean velocity, so the fluid has a viscosity is 0.38 Newton second per meter square when v is equals to 1 meter per second and h is equals to 0.5 centimeter. When h is equals to 0.5 centimeter, the velocity is 1 meter per second. So what we have to do, we have to find out the shearing stress acting on the bottom wall. This is the bottom wall. We have to find out the shear stress at this point. The shearing stress acting on a plane parallel to the walls and passing through the center line. And we have to find out the shear stress also at the center. Also at the center we have to find out the shear stress. So here, as you can see, this is the center line and this is our maximum velocity, that is 1 meter per second. We know the velocity at this point is 0. At the bottom we know, because in during the derivation of the Newton Law of Viscosity we always consider that the bottom plate which is fixed, the velocity is 0, and the top plate, if the top plate is also fixed, that means the velocity is also 0 here, and it is also showing in the velocity profile. Okay, this is the velocity profile, and at here there is a maximum velocity. You can see the line. This is the maximum velocity. The velocity is reducing, velocity is further reducing, and here the velocity is 0. So we have to find out the shear stress at this point, and we have to find out the shear stress at the center. So let's move on. So here we know the Newton Law of Viscosity for the Newtonian fluid, because they are saying it is the Newtonian fluid. For the Newtonian fluid we know the law tau is equals to mu du by dy. So the profile which is given, u is equals to the profile which is given, that is u is equals to 3v, okay, and u is the function of y. U is the function of y. So to find out the shear stress, we have to find out du by dy. Okay, mu is constant, we know the viscosity is given, so we have to find out du by dy. So let's move on. So here we to find out the shear stress, we have to find out du by dy. So next, so thus if the velocity distribution u is the function of y is known, the shearing stress can be determined at all points. Okay, once you find out an equation, so we can find out the shearing stress at all points by evaluating the velocity gradient du by dy. For the distribution given, so after the derivative, du by dy will become minus 3uy h square. Okay, so if you want the shear stress where h is equals to 1.5, you can calculate, and if you want to find out the shear stress at the middle point, you can calculate the shear stress. Okay, so this is the way you can find out. So let's move on to the question number 2. Question number 2, the sled shown in figure slides along a thin horizontal layer of water between the ice and the runner. Okay, so this is the runner, okay, and this is the cart basically which is used to move on the ice. So at the bottom consider there is a ice, so between the ice and this cart runner there is a water. There is a small thin layer of water. The horizontal force that the water puts on the runner is equal to the 1.2 pound. Okay, so the force exerted on the water is 1.2 pound when the sled's speed is 50 feet per second. The velocity of the runner or the sleds is 50 feet per second. The total area of both runners in contact with the water is 0.08 feet per square. The viscosity of the water is given. This is the value of the viscosity. Determine the thickness of the water layer under the runner. Assume a linear velocity distribution in the water layer. So first of all, here basically consider this is your ice, the bottom one, and this is the runner. So this is the runner which is moving with the velocity of 50 feet per second. So this is considered as a 50 feet per second, and this is your ice which is stationary. Okay, so the shear, okay, and it is moving with the velocity 50 feet per second, and there is a force acting on the top of the fluid which is 1.2 pound. Okay, so what exactly we have to do? We have to find out the thickness of water between the runner and the ice. So this is the runner and this is the ice. So we have to determine D. We have to find out the thickness which is D. So we know that the according to the Newton Law of Viscosity, tau is equals to mu dV by dy. Okay, so the distance between the runner and the ice is D, that we have to find out. Okay, so the maximum distance is D, that is D, and the velocity is moving, it is V. So tau is equals to mu V D. So if we know the tau, so we can easily find out the value of D. So we know that what is the tau? Tau is the shear stress which is equal to force per unit area. So from the force per unit area we can solve F is equals to tau into A. Okay, tau is equals to this, so we put the value of tau here. So V is equals to, so finally the F gonna become mu Vd into A. So F is known, mu is known, area is known, and velocity is known, so we can easily find out D. Okay, because here the shear stress was unknown, but the force was given and the area was given. So we by using this we convert the shear stress into shear force. So finally we separated the D and we put all the values, and finally we end up with 11.7 into 10 to the power minus 4 feet. It's a very small thickness of the film. So now let's move on to the another problem. So what is the calculate the dynamic viscosity of an oil which is used for lubrication between a square plate of size 0.8 by 8 meter and an inclined plane with an angle of inclination 30 degree as shown in figure. The weight of the square plate is 300 Newton and is slide down the inclined plane with a uniform velocity of 0.3 meter per second. The thickness of the oil film is 1.5 meter per second. Okay, so this is basically a ramp, and there is a oil, its thickness is 1.5 mm, and there is a square plate on it, and it's on the ramp, and it's moving with the velocity of 0.3 meter per second. It is given. So what we have to do, we have to calculate the dynamic viscosity of the oil. Okay, so we have to calculate the dynamic viscosity of the oil. So we are considering the Newton's law of viscosity. So what is the Newton's law of viscosity? So first of all we made the available data. So area of the plate is given, angle of inclination is given, weight of the plate, weight of the plate is given, which is acting downward, and velocity of the plate is given. So we have to find out, and the thickness of the film is also given. And as I said to you all earlier, you must convert all the unit in the homogeneous way, in the same system. Okay, so before it was in a CGS system, so we converted this unit into SI system in meter. If you do not do that, what will happen? You will get a wrong answer and you will surprise with that. Okay, so here we will consider the Newton's law of viscosity. So what is the formula of the Newton's law of viscosity? Tau is equals to mu du by dy. Okay, so here what are we have to find out the dynamic viscosity. So this is the dynamic viscosity. So we need, so what other things we should know? We should know the shear stress, we should know the velocity, and we should know the thickness of the film. So tau, how we can find out? We know the area of the plate, and the force is given, but 300 Newton is the force. So let's go back to the previous slide. So 300 Newton is acting vertically downward. So this is not the force which is basically producing a shear stress. Okay, the shear stress is always, the force must be acting parallel to the surface or parallel to the film. So this is the parallels, this is the surface, and we need this force in this direction. We don't need force in this direction. So we have to find out the force in this direction. So angle is given. So if we make the component of this force, so it will become two components, one x and one y. So this is this component of force basically is producing the shear stress. So what is that component? That is component basically is W cos 30 degree. If we take it, W cos 30, so this is the component in the direction of the fluid, okay, or in the direction of the slope, or in the direction of the velocity. So this is the force which is basically producing the shear stress. So what is that force? That force is W cos 60 degree. Okay, so if we multiply with that, so we'll end up with 150 Newton. So this is the force basically is producing the shear stress. So from here we calculated the shear stress, 150 over 0.64 is the area of the plate acting on it. So we got the shear stress. So we put the shear stress here and all the values are known. So we end up with the dynamic viscosity is 11.7 poise, or 1.17 Newton second per meter square. So here there is an example of the bearing, because the fluid is basically in a circular shape object. So this is the shaft, and this is the fixed end. This is the bearing which is fixed, and the shaft is moving, and in between there is a fluid. If this is the case, then and the shaft is rotating, so how we can find the viscosity? So this is also basically called a viscometer. So viscometer basically helps to determine the viscosity of the fluid, and this is the formula used to determine the viscosity of the fluid. So this is the formula, Fr and mu is equals to this and this, so that we can use directly. So omega, we converted this omega into 2 pi n. Okay, so 2 pi into frequency is equal to the angular velocity. So if we convert this, W is equals to 2, n dot is the RPM, 2 pi n dot. So you will end up with this equation. So let's move on an example which is based on this equation. So here basically the viscosity of a fluid is to be measured by viscometer constructed of 40 centimeter long concentric cylinder. So this is the cylinder is given. Okay, the outer diameter of the inner cylinder is 12 centimeter. Okay, the outer diameter is given, and the gap between the two cylinders is 0.15 centimeter, and this the gap is also given. So gap means the thickness of the fluid is also given. The inner cylinder is rotated at the RPM of 3000 rpm, 300 rpm, and the torque is measured to be 1.8 Newton. The torque is also given, so determine the viscosity of the fluid. So we know the formula of it. The torque is given, the length is given, the rpm is given, okay, the r is given, all the datas are given here. So just we need to insert the value, and we can calculate the viscosity of the fluid. So now, prior to start the surface tension, we have to discuss, or we have to understand some of the important terminologies of the fluid, that is cohesion and adhesion. What is cohesion and adhesion? Basically both are almost the same terminologies. The cohesion and adhesion both are due to molecular attraction. Okay, these are two different properties, but it is due to the molecular attraction. What is basically the cohesion? Cohesion force is the force between molecules of same medium. Okay, so what it does, cohesion enables liquid to resist tensile stress. Okay, and adhesion is a force acting between surfaces, between molecule of two different surfaces. And what it does, adhesion enables liquid to adhere to another body. Okay, just like water and glass. And in cohesion we can give an example. In cohesion we can give such as mercury and glass, because the mercury doesn't stick with the glass due to the cohesive forces between the molecule of the fluids. Now the other terminology is wetting and non-wetting. This is a very common terminology normally we use whenever we study the surface tension. So what is wetting liquids and what is non-wetting liquids? So wetting is basically means the wetting liquids are those which wets the solid surface when comes in contact with it. So how it happens? If the adhesion force, okay, what is the adhesion force? Adhesion force is the force between the two different surfaces, between the two molecule of different surface. When the adhesion force is much greater than cohesive force, the liquid will wet the solid boundary. Okay, such liquids are called wetting liquid, such as glass and water. When we drink water, we can see the part of the water droplets will still be present on the glass. That means there is a cohesive force is more than the adhesive force is more than the cohesive force. Because of that, the water droplets are stick with the glass surface. So now the non-wetting liquids, in the case of non-wetting liquids, the cohesive force are much greater than adhesive forces, and such fluids in which the cohesive forces are greater than the adhesive force are called non-wetting liquids, such as glass and mercury. So we can see the thermometer is a very good example of it. When we rise the temperature of the fluid, when it comes down, when it's cooled down, the fluid doesn't stick with the surface of the glass. All the fluid comes down because the cohesive force between the molecule of the fluid is more stronger than the adhesive force. Because of that, it doesn't wet the surface of the liquid. So how we can know that whether the liquid is wetting or non-wetting? To know whether the liquid is wetting or non-wetting, we have a technique or procedure to find out. So what we do normally to observe whether the fluid is wetting or non-wetting, we drop a liquid drop on the surface, on the solid surface. Okay, so if the drop of liquid comes with this shape, okay, so what we do, we draw a tangent with the solid surface and at the edge of the water, at the edge of the fluid droplets. Okay, so if the angle is less than 90 degree, okay, if the angle is less than 90 degree, such fluids are called such liquids are called wetting liquid, because you see it's spreaded on the surface, so such wetting liquids are called wetting liquid. So it happens in the glass and water. So now there is another case. So we put a drop of water on the surface, so and we make a tangent on the edge of the water droplet with the solid surface. If the angle is greater than 90 degree, okay, if the angle is greater than 90 degree, such fluids are called non-wetting liquid, because it's not wetting the surface. You see, it is just touching the surface, is staying. It's the cohesive forces are much stronger between the molecules comparing to the adhesive forces, but in the wetting liquid the cohesive forces are much stronger. Because of that, they are stick together. So this is the technique to find out whether the liquid is wetting or non-wetting. Surface tension and capillary effect. We all have seen these pictures, not only the picture, or we all have seen this phenomena in our daily life, not only in these pictures, but we all have seen this. The water droplets on the leaf and the water striders are floating on the water surface. So why this all happening? It's all because of the surface tension. What is basically the surface tension? The surface tension, there's a pulling force that causes this tension, acts parallel to the surface, and it is due to the attractive force between the molecules of the liquid. The magnitude of this force per unit length is called surface tension, and it is measured in Newton per meter. So basically, all the molecules on liquid surface experience a net inward pull, because of which there is a tension in the surface which is known as surface tension. So surface tension is due to the cohesion between liquid particles at the surface. So let's move on the next slides, where we can see how basically the surface tension phenomena occurs. Here you can see the water particles, and here is the surface. So this surface is called basically a free surface or liquid vapor interface. So this is the atmospheric, where there is a water vapors or air, and here is the fluid, here is the liquid. So this is called the liquid vapor interface or free surface. So what is basically the free surface? How we can define the free surface? The surface which separates the liquid and vapor, or surface open to atmosphere. The surface which is open to atmosphere, it is called a free surface, and in that case there is a normal force acting on the free surface, that is called a atmospheric pressure. Okay, and there is a zero shear stress, no external force in tangential direction. So because the fluid is stationary, there is no tangential forces acting on it, so there is no shear stress on it. So let's consider there is a fluid inside a container. So we can observe that the fluid particles in the within the fluid, and the fluid particles at the surface of the liquid. Okay, the particle which is within the fluid, consider the particle B, it is, you can see from all the directions the acting force are balanced. Okay, so that is called, this is basically the forces are symmetrical. So net resultant of force acting on the fluid particle is 0. Okay, but the fluid particles which are on the surface, we can see this is not balanced. The forces are asymmetrical. The net resultant force are not 0, and all the forces are acting downward. Okay, so because of that there is a pull force acting downward, so we can say that all the molecules on the liquid surface experience a net inward pull. Okay, net inward pull, because of which there is a tension, there is a tension on the surface, which is known as the surface tension. So in this case, this interface appears like a stretchable membrane, and there is a force acting tangent to the surface, that is basically the surface tension. It is indicated with sigma. So this is due to the phenomena called surface tension, and it can mathematically it can be written as sigma is equals to force per unit length. It can be measured in Newton meter. Okay, the magnitude of surface tension decreases for liquids, decrease with increase in temperature. So that means the surface tension force is the function of temperature, and surface tension are usually seen when the fluid comes in contact with the air. Only when there is a liquid vapor interface. If there is a liquid vapor interface on a both side, so we can observe the surface tension phenomena on both sides. That means there is a force acting from this side and the force acting from this side as well. That means 2F. Here you can see more clearly in the picture. This is the symmetrical, the forces acting on the particle symmetrically, and here the net force acting on it is symmetrical. So here you see there is a surface. Here there is a rigid wire frame. This is a rigid wire frame, and there is a kind of a film. When we pull this wire, when we apply some force, so there is an energy in the surface, there is an energy in the fluid film which opposes this force. Okay, so this force is basically resist with the effect of phenomena of surface tension. That means the rigid frame is open to atmosphere from this side and from that side as well. So there is a surface tension forces acting on this side of film and the other side of the film as shown in the picture. So that means if you want to calculate what is the amount of this force, so this sigma F is equals to force. This is the applied force acting over 2b, yani it's acting this side as well as other side. Okay, so sigma S is equals to force acting on this area and as well as other area. So this is the force which is basically opposing this force, and we can also calculate the work done, the applied force multiplied by the covered or the travel distance. The travel distance from here to here is delta x, the force into delta x. So what is the force we calculated that opposing this applied force? That is sigma S into 2b. Okay, so sigma S into 2b into x. So this is basically equal to, so this is equal to sigma x into b, length into width, that is basically equal to area. So we can say that surface tension, the work done per unit increase in the surface area of the liquid. So that in this way also we can explain the surface tension as we mentioned in the previous slide, the surface energy. The effect is also called surface energy, and it is expressed in the equivalent unit of Newton meter per meter square. So same here, this is basically the Newton meter per meter square. Sigma is basically the Newton meter square. Okay, so this is the unit Newton meter divided by meter square. Okay, so this is basically the definition of the surface energy. So now we move on to the application or effect of surface tension. It is seen in case of water droplets, water bubbles, soap bubbles. When a liquid droplet separated from the source, the liquid droplet takes up the shape of a sphere. Surface tension will try to minimize the surface area where as pressure will resist this. Due to decrease in surface area, the pressure inside the droplet is increases, and it keeps on increasing until both comes in equilibrium. In this manner, the droplets assume spherical in shape, which is having minimum surface area. As it is mentioned here, two kind of bubbles. Okay, one is for the air bubble and other is the soap bubble. Air bubble or the water droplets. So we have two cases here, the water droplet and the soap bubble. So how we can calculate the pressure and surface tension in the soap bubble and the sphere? So by controlling this, we can control the size and shape of the water droplets as well as the soap droplets. So in the first case, we are considering we have a water droplet or air bubble. In the case of water droplet, okay, in the case of water droplet, we know that the water droplet is full of liquid. It is full from inside, so there is no air space is inside. Only there is one open, one free surface which is outside the water droplet. That is basically atmospheric pressure. So in this case, there is two kind of pressure. There is a atmospheric pressure, that is outside pressure, and there is a inside pressure. So what should be the difference of pressure to maintain the shape and size of the water droplets? Because if the delta P is drop, what will happen? The bubble or the drop will collapse. To maintain the shape and size of the bubble, what should be the delta P, what should be the surface tension of the fluid to maintain it, that we can calculate by using this formula. So here you can see the force inside and force outside. Okay, so that we can calculate here. So this surface tension force which is acting on the surface of the soap bubble, so we just to see the way the force is the surface tension force is acting on it, we cut the water droplet into half. So this is the surface tension force which is acting throughout the outer surface of the water droplet, and there is a force which is balanced this force, that is basically the pressure force. Okay, so this is the pressure force and this is the surface tension force. So calculate the surface tension force, the sigma multiplied by the what is the force? The surface tension force is equal to force per unit length. So if you multiply it by sigma s into length, so what is the length? 2 pi r. So 2 pi r is the length at which the surface tension is acting. So this force on the surface is equal to 2 pi r into sigma s, which is balanced with the delta P, the pressure inside the water droplet, multiplied by the area, because the force the pressure is equals to force per unit area. To calculate the force, that is pressure into area, so change in pressure, because of that the water droplets maintain its shape, multiplied by the area, that is pi r square. So the pressure into area is equal to force. So these two forces are balancing each other to maintain the shape of the water droplet. That is basically equal to this, and delta P is equals to P in and P out. P out is the atmospheric pressure, Pi is the inside pressure of the water droplet, that is equal to 2 sigma r into r. In the same way, There is only difference in the soap bubble and the water droplet. In the air bubble, because this is also empty, there is no water inside, so that means we have two surfaces. This is free surface and this is also a free surface, so that means we have a the surface tension is acting double on the surfaces. Okay, so because of this free area, and because of this is also free area, not the free area, that is because of the free surface. So that means this force is going to be double, which is equal to the pressure force, and then finally we will end up with forcing mass into R. So now remaining we will talk in the next lecture.